Hello everyone, my name is Kobe Hass and this is going to be the first of what I hope to be several example videos to help with your course Computer Science 230. I'll be going over 4 examples today, truth values, basic predicates, as well as 2 basic proof examples for you guys to try at home, as well as I'll be giving you the answers in this video. The idea for this entire video was meant to help give you guys some extra practice problems for you to do outside of homework and to actually see how another student would go through a problem for something if they have no idea where to start. With all that out of the way, let's get started. Starting off on our first problem here, we have determined the truth value of each of these statements if the domain of each variable consists of all real numbers. So of course, I want you guys all to try each of these questions before I actually go into the answers, but however you like to take it, it's up to you. For A, there exists an x such that x squared is equal to 2. Well, we obviously know that x squared is equal to 2. We can obviously determine a single x value by just taking the square root of both sides, so we get x equals the square root of 2. Now we only have to ask, is the square root of 2 a real number? Of course it is. It is a irrational real number. So in this case, A is going to be true. For B, there exists an x such that x squared is equal to -1. So we'll go into the same problem, -1. This is logically equivalent to x is equal to the square root of -1. Is this true or false? Well, what is the square root of -1? The square root of -1 is I, a very imaginary number that we use for some reason in calculus. I don't know why personally, but yeah, so this is actually not a real number, so B is going to end up being false following along the 2 examples we just had. For C, we have for all x, it satisfies that x squared plus 2 is greater than or equal to 1. Alright, so we can obviously come up with an example where this is obviously true. You plug in x equals 1, we get 1 plus 2 is greater than or equal to 1, right? You plug in x equals -1, you get 1 plus 2 is greater than or equal to 1, right? This is just 3 greater than or equal to 1 for both those examples. That's very simple. The major idea that this problem, or this one is trying to get across, is that this x squared, you could try in -500 for x and it'll still work just fine, right? Because the squared is going to turn anything negative into a positive. So all we have to look for is the other 2 things. So we have 2 is greater than or equal to 1 in this case, because even if x is 0, which is its smallest possible value, it's still going to be true because 2 is greater than or equal to 1. So in this case, C is also true. For D, for all x, it satisfies that x squared is not equal to x. Is this true? Well, 0 squared, and all you need to disprove is just one example where you disprove the entire statement. 0 squared is equal to 0, right? So then this satisfies that x equals 0 is an x that does not satisfy this truth value, so, or I guess predicate. So in this case, D is false. And this would also work for if x equals 1. All right, with that, we are all done, and we'll go on to the next problem. Going on to our second problem here, we have let q xy be the statement x plus y is equal to x minus y if the domain for both variables consists of all integers. What are the truth values? So we go on to A here, B, C, actually I'll write it how they have it in the problem there. B will be over here, C, D, E, F, G, H, and I. All right, so if our statement is x plus y is equal to x minus y, so then if we plug in 1, so does 1 plus 1 equal to 1 minus 1? This is obviously no, because 2 does not equal 0 in this case, so A is already false. B is 2 plus 0 equal to 2 minus 0? This is actually true for basic math that I am definitely good at. So going through these first two problems, it seems like we're going to be doing a lot of like something plus something is equal to something minus something. So we can actually do our best and actually simplify this statement up here to be something we want. So over here, we have the statement again just rewritten, and we're just going to cancel out the x's here. Okay, so we're going to be left with y is equal to negative y. And for any integer value, and since y has to be the same 1, you can't have 1 equal to negative 1 in this case. So what we're going to have to do is we have to say that the only way this could possibly have a truthful answer is if y is equal to 0. And so we can apply this logic for the future questions here. So for C, for all y, q1 comma y. And so this is the same thing. For all values that y is possible to have, we've proven that there can only be one possible solution for y. So by saying for all y, we can plug in 50 and it could work. In this case, it will not, so C is going to be false. D, there exists an x such that q of x comma 2 is true. This here, again, we've proven that any value of y that is not 0 will not work. So automatically, just by seeing the 2 there, we can say that this is going to be false. E, there exists an x such that there exists a y that q of xy is true. And we already know this is true because we're just saying that there exists an x and a y such that this is true. And we already have a proof for that up here, where x is 0, or any number, or 2 in this case, and y is 0, right? That's what B was. We had an x is 2 and a y is 0. So we know that E is true. F, for all x, there exists a y such that q of x comma y is true. And again, just like how we made the argument up here that only y had to be 0 for it to be true, we know that this statement, since we have a changing x and then changing y, if you want to think about it like a double for loop, we have our y being found after deciding the x. So in this case, it does work. So yeah, F is going to be true. G, there exists a y such that all x, q of xy is true. Again, we've said that all you need to do is find the y, and we're just going to spin through all the x's to find the answer. So G is going to be true. H, for all y, there exists an x such that q of x comma y is true. Going along the same lines, we've proven that y equals 0 is the only possible solution. So if we go cycle through every single y possible, we're going to hit a non-zero number. So H is going to be false. I, for all x and all y, q of xy. This, again, we've found the same argument as before. We can't rattle through every single number of y because only 0 works for this. So by just having for all y, we immediately get a false here. All right. If you have any questions, don't come to the help room, make a post, or just send an email. We'll be happy to help resolve any questions you guys have about this. On to the next one. On our third problem here, in our first proof problem, we have that prove that if x is an odd integer, then 9x plus 5 is even. And going just straight into it, it'd be kind of confusing because, yes, we'd have that, of course, x is odd, right? But we'd have a very difficult time figuring out, okay, how can we prove is 9x plus 5 even? Because this is an odd plus an odd, right? So instead, what we're going to have to do is pull out something that was taught in one of your recent lectures, that all odd integers can be defined by a simple equation that x, in this case, is going to be equal to 2 times an integer plus 1, where, of course, 2 times anything is going to be even, right? And so since we know that x can be replaced with 2k plus 1 for an equation of itself, we can do that. It's the same for the 9x plus 5 up there. So instead of 9x plus 5, we'll get 9 of 2k plus 1 plus 5. Just multiply that out real quick, and we'll get a 18k plus 9 plus 5, and then you'll end up with 18k plus 14. And of course you can take out a 2 here, which this is what we're hoping to get because we need to prove that it's an even number. And one of the simplest ways to get an even number is to prove that it is a multiple of 2, or it's able to be divisible by 2. So in this case, we pull out a 2 out the front, and we get 9k plus 7. And just right there, because we're able to pull out a 2 from the equation here, then we know that this is going to be a multiple of 2. I understand this isn't a completely formal proof, however, it's more or less getting into the idea of it. When you guys do proofs, you might have to use rules and laws, but this is a good introduction proof to help you guys get into the feel of what you might have to do. And with that, we're done. On to the next one. All right, and to our final question, which is going to be a proof, is suppose we have a list of integers a1 through a6. Prove that at least one of these is greater than or equal to the average of these numbers. 1. So, and we even give a hint here, try a proof by contradiction. And if we ignore that hint for right now, and we just try to give a normal proof like we did before, we'll come to a roadblock right away because we can't assume what we're trying to prove. So like if we say that a1 is greater than or equal to the average, we're already wrong because we cannot assume what we're trying to prove, right? Because we're just trying to prove that one of them is greater than or equal to the average, so we can't just assume our provocation right away. So instead, what we have to do is we have to kind of take a back road to this, so we have to try a proof by contradiction. And to give a little reminder of how a proof by contradiction works is we assume the opposite. So we assume in this case that none of them are greater than or equal to the average. All right, so A1, A2, A3, A4, A5, A6, not a single one of them is greater than or equal to the average, which we logically know as decent mathematicians that this is completely false, but we still need to prove it. And so with this, if we follow along with this, we get down to a point, we do a couple steps, logical steps that we know are completely true, end steps until we get to the end and we find that, say, 1 is equal to 2, right? Then we find that, well, we took logical steps down here that we all know are true. All of these are true. We did not take one wrong step along the way, so that means that the only thing that could be wrong is our assumption. And that's how a proof by contradiction works. You assume something and you follow along a path of truths to find that you get a completely incorrect answer, in which you find out that your assumption itself was wrong. So we'll go along with that. I did not go over this problem, so I don't know the exact path to take right away. So we'll just write out what we know. So we do know with our assumption here that A1, A2, A3, A4, A5, A6 are going to be less than the average, because they can't be equal to in this case because of that. And we get that it's going to be less than A1 plus A2 plus A3 plus A4 plus A5 plus A6, all divided by 6. This is just the definition of an average, and that's how we get here. And so this is about all I know for the information that we're given. And the one thing I would try right away is, you don't really want to subtract these together. This is what we're working with, A1 through A6. So I'm just going to add these all together. So that means we have, if we add, say we add A1 plus A2 from this definition on this side, then we have to make sure that it's less than 2 times the average on this side, all right? Because we have two values which are guaranteed to be less than this. So we need to have A1 plus A2 is going to be less than 2 times this whole function. So if we instead do that for, say, all of them, A1 plus A2 plus dot 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 plus A6 is going to be less than 6 times our sum here, all divided by 6. And this is actually the correct path. Okay, then we'll end up with A1 plus dot 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 plus A6 is going to be less than A1 by canceling out the 6's here. A1 plus dot 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 plus A6. Taking logical paths here, we know that adding A1 plus A2 after our assumption here, we know that this has to be less than 2 times the average. And that's the same thing if we add all 6. So A1 through 6 has to be less than 6 times the average, right? And in this case, we get to here, where our sum is going to be less than our sum. And this is completely false here. We can't have a number being less than itself. So we know that by taking logical, truthful steps, we know that our assumption then is false by default. All right. I hope you guys had some useful experience from this. I'm hoping to be able to do this more often. If you guys have any questions that would like to be covered, you guys can post them in the Runtime Terror Discord. You've also got your professor. You can ask her. One second, I'll look this up. Professor Soma. You can send her questions. You can send them directly to my email, which is kjhass at iastate.edu. Anything you'd like me to cover in these kinds of videos, I'd be happy to. It'd be very helpful to have some kind of questions. And if you guys have any questions over the class, you guys have recitation hours, you have office hours, you can email your professor, you can stop in the help room. Anything you can do to help you understanding the material will be great for the coming weeks that you guys have. Yeah, I hope you guys found this video very helpful, and I'll see you next time. Have a good day, guys.